start. So the speaker is Zorin-Kranich from Bonn, and he's going to speak about variational estimates for martingale transforms.
Yeah, so thanks to the organizers for setting up this online event and also for the invitation. So I will talk about variational estimates for martingale transforms, and the title of this talk is intentionally very similar to the title of my last year's talk, which had, instead of martingale transforms here, martingale paraproducts. And okay, this is a joint work with Peter Fritz. So just to set up some, just to say what is my formal setting. So I work with rough paths whose regularity I measure in p variation. And the variational exponent will be between 2 and 3. So this is at the level of martingale rough paths, so that I view them as a pair of process X and an area term Blackboard Bolt X. And okay, they always assume to satisfy chance relation and so on. And this is just to recall the definition of the p variation. So by the way, I forgot to post the link to my presentation. I posted to the chat now, so that you can go back and forth. Okay, and the basic question that I'm addressing is how to construct such paths, so how to get these conditions for some paths of interest. So here is an answer for martingales, which you probably all know very well. If you have a martingale, which I assume is Cadillac and has values in a Hilbert space, this sometimes causes some confusion. You can assume that it's just real valued. And then if we look at this area integral, then the pair consisting of a martingale and the area integral is a rough path of regularity p for any p strictly greater than 2. Okay, so what there are several parts in this claim. There is chance relation, which is just the fact that these integrals add up like this. So if you have here 2 integrals, then to make an integral of the union of the intervals, you just have to add this small square. Then there is the p variation bound for the martingale M itself. This was proved by Lépingle in 1976. And then you need bounds for the p half variation of the area term. And this was the basis of Lyon's work introduced in rough paths, the observation that such a bound holds for Brownian motion. For more general martingales with continuous paths, this was proved by Fritz and Victoire using basically an extension of Lépingle's argument. Now, I come from harmonic analysis, and in our community, Dolmus, Kaller, and Thiele proved such an estimate for dyadic martingales. So this means just that the space is R to the n, and the filtration consists of sigma algebras generated by dyadic cubes, whose size is the generation of the sigma algebra. Okay, and now for general martingales with Cadillac paths, such a variational bound for the area term was proved by Cheverev and Fritz in 17 using the Lépingle's argument, and Viekovic and myself gave a different proof of a more general result in 18, well, coming from this harmonic analysis picture. Okay, so here are some remarks that maybe you can have, maybe some of you have some suggestions for me. What are the most interesting, or what are our interesting classes of processes that one could look at? For instance, there are such variational estimates for area terms of Levy processes in a paper of Williams, I think. So maybe you can tell me what else one could look at. So here is some newish result, which should be published soon. Now we start with a given deterministic graph path, which let's call it X, and the Martingale. And now we can construct a joint lift of this pair to a graph path. Well, for this you need to specify the array terms of this process. And okay, the array term where you integrate X against itself should be the array term of the original path X, but then all other things are some integrals. So these two are E2 integrals, and this is a kind of new integral where you integrate Martingale against a deterministic path, but yeah, this is not yeah, okay, there are some difficulties with defining this because this is not a usual Young integral. Okay, so what is the motivation for doing this? Well, one motivation is that maybe you want to solve some kind of mixed differential equation where you have a rough and a Martingale driving part. In fact, if you want to do this, then this result basically allows you to do this pathwise. If you don't want to do it pathwise, there is a different theory which then allows you to use coefficients B of lower regularity, which is being developed by Peter Fritz, Collet, and Antoine Wauquiez. All right. Now the qualitative result here is not entirely new. There was a paper by Tal Orenstein, Nicholas Perkowski, and what was I don't know the third person personally, so I don't remember the name, where they make some qualitative construction of this kind, but it doesn't come with optimal estimates. And our theorem comes with optimal estimates. And so what are these quantitative, new quantitative things? These are optimal variational estimates for these kinds of integrals, and also the construction and estimates for integrals of Martingale with respect where the integrator is a rough path. All right, so all our results in continuous time are deduced from results in discrete time by some approximation process. And this is our main result in discrete time. So now instead of process X, we have a discrete time adapted process, which is now called F instead of X, because it's I wanted a different letter in discrete time, and the Martingale is now called G. And what we call paraproduct is a kind of discrete area integral. So yeah, if you replace this sum sign by an integral sign, then it looks basically exactly like an area integral. Okay, Oh, thanks, Tal. The third person on your paper is Jean-Dominique Deutsche. Or, yeah, I'm not sure if I'm pronouncing this correctly. Deutsche. Thanks. So, and the main estimate in discrete time is the following. So, we can estimate the pointwise R variation of this paraproduct by product of two norms of the G martingale and the F process. So for the martingale, I take just the square function. So you see my pointer, right? Okay, I assume that you see my pointer. Yeah. So this is well, the square root of the square bracket. And this thing that depends on F is maybe a little bit more interesting. So there are two cases. If F is itself a martingale, then what do we see here? Here is a supremum over some subsequence of times. And then basically you can use a kind of vector valued BDG inequality to replace this supremum here by square sum. And then you can take this P equals to 2, and then what you get here is also just the square function of your martingale F. So then you can take P equals 2, and the condition on this R becomes R is less than 1. So this is recovers the variation norm estimate for the integral of a martingale with respect to martingale. Or you can take a general process F here and then just say that this is P variation, or bounded by the P variation of your process F. There's also this supremum of increasing sequences of stopping times, which is important, but maybe you can also ignore it for the first reading. Okay, and in this case of general process, when this is the P variation, then this condition on R allows you to take R equals P half. And this is exactly the regularity that you want for the A-ray term of your graph path. So here is a small slide about how to pass from the discrete to the continuous. I don't want to say much about how you do this for integrals, but for processes, this is pretty easy. So if you have an increasing sequence of stopping times P, then you can discretize a given process by just making it constant between the stopping times. This is what this notation means. And then it turns out that these discretizations converge to the original process when, well, in a certain sense, which is sometimes called refinement sense. So if so, there exist arbitrarily fine partitions so that the discretized process is close to the original process, and the important thing is the space here. If the original process was in LQ in probability with values in P variation in time, then this convergence is in LQ in probability and P tilde variation in time for any strictly larger P tilde. So how do you see this? Well, uniform convergence is pretty easy. You just take the stopping time so that between stopping times you do not change more than by epsilon. But if you have this with infinity variation, then you also get all the variation exponents between P and infinity just by some cheap Herder inequality. Okay, and this is basically the idea for approximating continuous things by discrete things, and the convergence will be always in whatever sense your discrete estimates are given, because basically this convergence in LQ VP tilde always propagates through all the estimates. So this is how you convert this discrete time estimates into continuous time estimates. Okay, and then I can say a few words about the techniques that we use. So our main objective is the following, is this estimate here. So we want to bound the R variation of something, and the variation is inside the LQ norm. And there's a stopping time argument which allows you to get rid of this R variation inside in some sense. So I will not show the argument, but what it effectively does is that here you have some supremum over all increasing sequences of times inside the norm, and after this stopping time argument, this supremum goes out of the norm. There is a small price that you have to pay, that here you have to decrease your exponent so that you get a somewhat larger quantity. And there is also another price that you have this extra supremum here. So previously you would have here, oops, I clicked in the wrong place. So previously you would have here maybe also taus, and now you have this extra supremum. Well, you have to live with it. So this, okay, here is one of the early consequences of this argument. So this kind of stopping argument, so I introduced this stopping argument in a paper last year, where I was proving a refined version of Lépingle's inequality. So what does this so let's read it. This is a martingale here, M, and we have LP norm in probability, and on the left-hand side we have the LP norm in probability of the R variation of this martingale, and the variation exponent is greater than 2. So this is Lépingle's inequality, but the version that I proved also has these weights here, and maybe you don't have to know what the condition on the weights that you have to put here is, but you can quickly check that if your weight is just constant 1, then this expectation is constant 1, this expectation is constant 1. You're taking that infinity norm, you get constant 1. So basically then this thing here is 1 if W is 1. But there is a big advantage to this kind of weighted inequalities. And the advantage is that they allow you to deduce vector valued inequalities. Well, we do not need, so in our newest work with Peter, we do not need the vector valued inequalities that you get from this result, but we do need a vector valued version of the BDG inequality. BDG is Burkholder-Davis-Ganti, right? We deduce from some weighted inequalities by Ossikovsky, which are also pretty recent, 17. I think you can also get this vector valued inequalities by some other methods, but now that we have weighted BDG, this is actually very simple. Okay, now I was talking a bit about vector valued inequalities, and I want to actually illustrate how they're used, but I will not do this on the sophisticated problem of Ito integration, but rather on a simpler problem where we look at some square bracket. So I recall that at the beginning of the talk, I was saying that I will lift a pair consisting of a rough path and the martingale almost surely to a joint rough path. So what we have looked at so far is what is this term, integral of x with respect to m, and then also integral m dm is very similar. And what we haven't looked at yet is the integral of m with respect to dx. And well, how do you construct this integral? Well, you do this by partial integration. So these are the boundary terms. This is the integral of x with respect to dm. And then there is this bracket term. To make sense of this, you should first do this for discrete approximations. But let's say that we have already done this. Then what comes out is that you need some kind of bracket term here, and this bracket term is in fact the following. It's the sum over all jumps of your path x of jump of x times the jump of the martingale. Recall that everything that all my processes are CAD-like. So this is in fact a non-vanishing quantity if they jump at the same time. So how do you get a variation norm estimate for this thing? So first you apply this kind of stopping argument to get rid of this variation. So this variation, it has some supremum of increasing sequences, and this supremum goes here. And then I kind of forget it, so that I just fix an increasing sequence of stopping times. Yeah, maybe I should have written it here. So tau k, this is an increasing sequence of stopping times. And now, what do we see? So there is this supremum inside, and to make our life, yeah, okay. This quantity here is itself a sum of martingale increments. So these increments they are also martingale increments because x is deterministic. Well, you can also do something like this with x adapted and controlled, but for simplicity, let's take x deterministic. Then these are just martingale increments themselves. And now you would want to use BDG inequality to get rid of this supremum and replace it by some square sum. And the only problem is that you have this sum over, you have this extra little L raw norm inside. But vector valued Burkhalter Davis Gaussian inequality is exactly about this situation. It allows you to replace supremum by square function inside such a nested norm, which consists of, let's say, some LQ norm in probability and little L raw norm on top. Okay, and then you get a square sum here, and then you can pull out these increments with Hölder's inequality, and inside you get the square function of your martingale. So this is all I wanted to say about vector valued inequalities, and this is also the end of my talk.